Hi and welcome to the first video of the series, The Geometric Approach to the GCD. This video presents an alternative method to the extended Euclidean algorithm using a linear algebra approach to solve linear Diophantine equations. Let's start with a simple analogy. Imagine we have a cake and we want to cut it into square pieces. What is the size of the largest square we can use? This one? That one? Or maybe others? This question can be modeled to help us understand the concept of the GCD. Okay, let's represent the cake as a rectangle with sides A and B, and the square pieces as having side D. We can clearly see that A is equal m times D and B is equal to n times D. So D divides A and D divides B. This means that D is a common divisor of A and B. So the largest possible D is the greatest common divisor of A and B. However, at an event like an anniversary, we might not know the exact dimension of the cake. And even if we do, we might not know how to calculate the GCD directly. So how can we tile the cake with the largest possible square pieces? Well, this answer is simple. We follow the principle we stated. We want the largest square piece, so we start by cutting the largest square that can fit within the cake. And here, there is a remaining rectangle here. If we can fit another square of the same size, we continue until we obtain a rectangle that cannot fit this rectangle. Then we start the process again, and we cut the largest square that can fit within this new rectangle, and we continue until we obtain a remainder rectangle that cannot fit this square. And then we continue to applying the process until eventually we obtain a square, but not a rectangle. And the size of this last square is the largest square that we can cut into this cake. Because this square can fill these larger square and then also these other larger squares. But this process is in fact the Euclidean algorithm used to calculate the GCD of two numbers. Suppose that our rectangle has the sides 10 and 23. We start by subtracting 2 times 10 from 23, and we end up with the remaining rectangle of size 3 times 10. Then we subtract 3 times 3 from 10, and we end up with the remaining rectangle of size 1 times 3. And then we subtract 3 times 1 from 3 to obtain 0 remainder. The GCD of 10 and 23 is the last non-zero remainder. Okay, that was easy. Now let's take it a step further. We claim that if D divides A and D divides B, D will divide a linear combination of A and B. So D will divide AU plus BV, U and V being integers. The proof is pretty simple. D divides A mean that A is equal to MD. D divides B means that B is equal to N times D, M and N being positive integers. In AU plus BV, we replaced A and B by MD and ND, and then we can factor out D. Here we can see that AU plus BV is a multiple of D, meaning that D divides AU plus BV. We can write this relation as AU plus BV is equal K times D, K being an integer. And for the particular case of K is equal to 1, AU plus BV is equal to D, D being the GCD of A and B. This relation is known as the Bézout's identity, named after the French mathematicians Etienne Bézout. Okay, let's look at some examples. We saw that the GCD of 10 and 23 is 1. So there exist U and V such that 10U plus 23V is equal to 1. A particular solution to this equation is U is equal 7 and V is equal to minus 3. But since this is a line equation, we have infinitely many solutions for this equation. And this solution can be expressed as 7 minus 23k and minus 3 plus 10k, k being an integer. Another example, the GCD on 1050 and 2268 is 42. So there exists U and V such that 1050U plus 2268V is equal to 42. Again, a particular solution to this equation is U is equal 13 and V is equal to minus 6. And the general solution is represented by 13 minus 54k and minus 6 plus 25k, k being an integer. The Bézout identity works also for more than two numbers. As in this example, suppose that we have 17, 27, and 37, and their GCD is 1. So there exists x, y, z such that 17x plus 27y and 37z is equal to 1. Again, a particular solution to this equation x, y, z is 9, minus 7, and 1. And here we can represent two general solutions for the values of x, y, and z, represented here, where k1 and k2 are integers. More generally, if D is the GCD of A1, A2 up to AN, then there exist integers vi, v2 up to vn such that the sum over I from 1 to n of ai times vi is equal to d. These equations are called linear Diophantine equations. The standard method to find the vi's relies on the extended Euclidean algorithm, which, at least for me, feels more like a nightmare than an algorithm. And that's precisely the motivation behind this series of videos. The goal here is to explore an alternative method, one that is neither simpler nor faster than the extended Euclidean algorithm, but, again at least for me, far more intuitive and comprehensive. I won't be diving into how the classical extended Euclidean algorithm works. There are plenty of excellent YouTube videos explaining it with lots of colors, arrows, and OKs. Instead, let's bypass this method entirely and discover a new way to solve linear Diophantine equations. Now suppose there exists a linear transformation that maps a one-to-one square to an A times B rectangle. If we can find such an invertible matrix, its inverse will map the A times B rectangle back to a one-to-one square. For this matrix to work, it must satisfy two requirements. The sum of the rows must be equal to the side of the rectangle, and since we want integer values in the inverted matrix, the determinant must be plus or minus 1. And here we can see that something very similar to the Bézout identity for the expression of the determinant. Now, the rows of the inverted matrix are in fact two solutions to Bézout's identity. Using this matrix, we can construct the general solution of the linear Diophantine equation, where k is an integer. In a future video in this series, we will explore how to find the general solution to any Diophantine equation using this approach. But for now, we still don't know how to find u and v, and we aim to avoid using the extended Euclidean algorithm. However, since we are dealing with linear transformation, we can exploit the linearity of the GCD to find the solution. The linearity of the GCD implies that the GCD of A and B is equal to GCD of A and A plus B. Geometrically, this can be represented as adding a length of A to the rectangle of A times B. And in terms of linear algebra, this transformation can be represented using a matrix X, which is the extension matrix, where the determinant of X is equal to 1. Similarly, the linearity of the GCD also implies that the GCD of A and B is the same as the GCD of B and A plus B. And again, geometrically, this can be represented by a matrix, which is a rotation, and with the determinant equal to minus 1. Okay, now let's do some examples to see how we can use this elementary matrices X and R to build the overall transformation which maps the unit square to a given A times B rectangle. And here we are going through the steps of the Euclidean algorithm. In the first step, from the point of view of this rectangle, we are applying a rotation followed by an extension. So we can write the coefficient 2 as the product of X and R. In the next step, from the point of view of this rectangle, we are applying a rotation followed by 2 extension. And we can see here that this coefficient 3 can be written as X, X, and R. And note that this transformation will map this rectangle into this rectangle. And in the final step, from the point of view of this square, we are applying a rotation followed by an extension. So the 2 can be written as X times R. Then the overall transformation is the product of the transformations of the steps. So we have xr times xxr times xr, which gives 3, 7, 7, 16 matrix. If we apply this matrix to the vector 1, 1, we obtain 10 and 23, which is the dimension of the original rectangle. And when we inverse it and then we apply it to the dimension of the rectangle, so the vector 10, 23, we obtain 1 and 1. And the general solution can be written as 7 minus 23k and minus 3 plus 10k, where k is an integer. Now let's do another example, but this time without drawing the rectangles and following only the steps of the Euclidean algorithm. So here we have a quotient of 2 in the first step, and 2 will be written as xr. This means that the quotient n here, 2, will be written as n minus 1 x to the n minus 1 times r. In the second step, we will have a quotient of 6. So 6 can be written as a transformation of x to the 5 times r. And again, n is written as x to the power of n minus 1 times r. And in the last step, we have a quotient of 3, which can be written as x square r, and again n is x times n minus 1 times r. Putting all these together, we have xr times x to the power of 5r, x to the power of 2r, which gives the matrix 6, 19 and 30, 41. And if we apply this to the GCD of these two numbers, which is 42, we will obtain the 1050 and 2268, which are the original numbers. Then we inverse this matrix and we apply it to the original numbers 1050 and 2268, and we see that we obtain 4242, which is the GCD of 1050 and 2268. And the general solution is 13 minus 2268 over 42k and minus 6 plus 1015 over 42k. And since 42 is the GCD of these numbers, we can divide them and we obtain an integer, which leads to the general solution of 13 minus 54k and minus 6 plus 25k, where k is still an integer. Now let's summarize the whole process. We start by using the Euclidean algorithm to find the GCD of A and B. Then we transcribe each quotient ki into a transformation of x to the power of k minus 1 times r, except for the last step where the transformation is x to the kn minus 2 times r to ensure d as a remainder. The total transformation is the product of all these transformation, which gives the overall transformation for mapping the d times d square to a rectangle a times b. And the inverse of this matrix applied to the a and b will give the vector d, d. This means that the rows of the inverse matrix are the solution uv to the Bezout's identity au plus bv equal GCD of a and b. And here is the general form of the T inverse, and here we can see that the determinant of this matrix depends on k here. And n and k are integers. And we can note that this implies that the matrix T is not unique, and by tuning n and k, we can obtain an infinity of matrix T, which will, when inverted, gives the same solution. Okay, I hope you found this geometric approach insightful and worthwhile. In the next video, we will extend this method to higher dimensions to solve the Fountain equation involving n variables. Thank you for watching, and I look forward to your comments and feedback. Bye.